All right, before the break, we were looking at binary representation of numbers. Fairly straightforward. We saw there at the end, adding and subtracting in columns like we learned back in elementary school, where we carry things to the next column or borrow things from the next column over. However, we could build a machine that would do that, but we would have to build two circuits to do that, right? We have to do one for the addition that carries things to the next column, and we need a completely different circuit for subtraction where we borrow things from the next column. Doable, but it'd be a lot nicer if we could do it all from with one operation. Usually I show this a little bit later. I'm gonna jump out of order. So there's this old math trick that has often throws people off. But we use what's called 2's complement. Complement with all E's, not saying nice things about the colors, not saying nice things about our numbers, like the complementary colors. Things across the color wheel. Doesn't matter if we use magenta, yellow, cyan, or red, green, and blue. Complementary colors are still complementary. Yellow and purple are still complements of each other. Blue and orange. No matter where we got the color from, the complement of it, and the 2's here, it refers to like second degree complement. A lot of people only hear about it in binary because I'm going to do a very quick version to show that it works. Show what it is, and it's a mess in base 10. So it just sat around as just an interesting pattern that existed in mathematics. So we saw I'll use those same numbers we used earlier. 13 plus 7. Well, adding was fairly straightforward. 30 plus 7 is 10. So we write a 0, carry the 1, and we get back to 20. It would be nice if we could do our subtraction the same way. And we're able to. So if we wanted to do 13 minus 7, we could change that into 13 plus negative 7. Everybody's kind of familiar with that, right? So a complement, which is going to get a whole lot easier here in a second. We almost never do complements in base 10. Complement is how far we are from the largest number. Numbers are metric. Wait, I don't need to get into that. Starting to get into high level math stuff. We can measure distances between numbers. We can think of them as something we can measure. So we have a distance through our highest number. In base 10, 9 is 0 away from our highest number because it is our highest number. 5 would be 4 away from our highest number. So the complement is what we would add to get to the highest digit in our system, which is way easier in binary. And most people only hear about it in binary because it gets a little confusing. But if we take 2's complement, which is really the second degree complement, we would complement our numbers. So make all our columns line up. I'm going to switch negative 7 to negative 0, 7. That 0 up front doesn't do anything. Then I'm going to complement those. So 13, our 1's complement, which is really the we just take the complement of it directly. So our first number doesn't change. It's positive. It's just another way of writing the negative numbers. So 0 is 9 away from our highest digit, and 7 is 2 away from our highest digit. And then to get to the 2's complement, or sort of the second degree complement, because if we just complemented it again, we get right back where we started from. So to get the second degree's complement, we add 1. Third degree's complement, we add 1 again. For the four's complement, or might make more sense to think of it as the 4th degree, we would get to the 3rd degree and then add 1 again. So that just taking the complement doesn't get us back. So 9, 2 plus 1 would give us 9, 3. Then we have 1, 3 plus 9, 3 that gives us a representation of negative thing here. I'll talk about it in binary. It's a little bit easier in binary. I just want to show that it's an old trick because people always see the 2's there and think that it's something new for binary. It just mostly sit around in drawers and shelves. It's like, oh, that's neat. But now we can just add 3 plus 3 gives us a 6. 1 plus 9 gives us a 1, 0. And when we do this, we always have an extra digit. 13 minus 7 would be 6. So 13 plus -7, which we can represent as 13 plus 9, 3 using 2's complement, gives us 0, 6, and an extra digit, which we can just discard that extra digit. So an old math trick that we can, once we have negative numbers, we can just use this and do that. And complements are even easier in binary because we have 0 and 1, right? So we use that technical definition. How far away are we? A 0 is 1 away from a 1, and a 1 is 0 away from a 1. It really just becomes the other digit. So the complement is the other one when there's only 2. It's only one possible way to complement it. I was just doing this to show it works. It becomes a confusing mess at times in base 10. So it mostly just set on a neat little pattern, but it allows us to build all of our math from a single operation. Instead of add and subtract 2 different things, we have add and add a negative number. So we need negative numbers, which is no problem. Base 10, right? We just throw another symbol on there, right? A positive 13 and a -7 for that one we just did. We can do that with all our numbers. You all have seen that before. Usually when learning it, it's best that humans do best if we think about it as money. Positive numbers are money coming in, and negative numbers, money going out. Helps us to think about that stuff. So we could just throw a symbol on top of our binary. Let's stick with 13 instead. That way we can use the ones we found, those binary numbers we found earlier. Or let's do a quick practice, maybe one more practice time. Let's do 15 and 8. Those are 2 numbers we're going to use. So addition is still like it was. Somebody want to tell me how to write 15 in binary? I see you all thinking about it.
Zero, 1, 1, 1.
Yes. No 16s, but yes, an 8 will fit, which leaves us 7. So yes, a 4 will fit. 4, 2, 1. Oh, 15. Yeah. 1, 1, 1, 1. The 5th column would be our 16s column. Sorry. 8 will fit, plus 4, plus 2, plus 1. And 8, somebody want to tell me how to write 8?
1, that's all
0. Yeah. 1, 0, 0, 0. So there's the 2 numbers we're going to do some math with. We want to make them positive and negative. So let's say positive 15, 1, 1, 1, 1. And to make it positive, we just need to throw a symbol here like we did here. Let's use a 0 for a plus. 0 is defined to be plus, and 1 is defined to be negative. We only have 2 symbols, so we don't have to spend a lot of time thinking about what they are. Right, we're working in binary, so our switch is either on or it's all. We can't make up another symbol to represent one of those 2 states, or I guess we could, but we only have these 2 symbols. So positive 15 and negative 15 will be 1, 1, 1, 1, 1. So we're really still dealing with 4-bit numbers, but our 5th bit here is going to represent the sign, whether it's positive or negative. It's going to work for all of our numbers, almost all of our numbers, right? Positive 7, negative 7. Positive 137,219, negative 137,219. That works for almost all of them. We'd also end up with that situation, wouldn't we? zeros included in binary, so I can just write a bunch of zeros here. We'd end up with these binary numbers. We get two ways to represent zero, but on all our other numbers, two representations accurate. That's a little off for zero, isn't it? Because we only have one zero. There's not a positive or a negative zero. So having two of them is what's called the zero problem. And two's complement's the solution to that. I threw it out of order because I wanted to try working it in earlier. I usually show it at base 10 later, and it seems confusing there because we start talking about binary and we're ready to stick with the stuff that we use in computers. So the zero problem, two representations of this becomes a problem. But if we did two's complement on zero, we just saw what two's complement was. So 0, 0, 0, 0, 0. So I'll do a 4-bit one. If we complement this, we get 1, 1, 1, 1, 1. So there's our ones complement. And if we add 1 to it, we get the two's complement. 1 plus 1 is 2. So a 0, carry the 1. 1 plus 1 is 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 1, 0. And just like in base 10, we'll always have an extra bit when we do two's complement. And for the negative 0, we'd have 1, 0, 0, 0, 0. So if we complement that, we get 0, 1, 1, 1, 1. We add, oh, so there's our ones complement. Then we add 1 to get our two's complement. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. 1 plus 1, 0, carry 1. 1 plus 1, 0, carry 1. And we get right back to what we have. The extra bit's a 0 in this case. We do get that because it's a circuit. Every one of these bits is going to a certain connection, right? So we always have that extra connection. But we're looking at the 4-bit number. Right. Complement that, add 1. Yeah. So we're looking at that 4-bit number and we get back to the same 4-bit number. Why did that come off different? I think I might have defined it something wrong, but we get back to just one single 0 and then that extra bit. The 4 bits that matter both cancel out there. So we end up with just 1 0. Everything else would be a unique representation. That extra bit, if anybody's heading onto a 4-year program afterwards, or some point in your future, you end up studying machine language, that extra bit for us today, we're just going to discard it. But it is kind of a very important thing. So when you get to assembly language, that would be your jump on carry bit, the overflow bit. It's one of the most important classes through our CPU that we want to keep track of. Today, we're just going to discard it, which is really what happens in the computer. That extra bit just goes to ground. The electricity just flows back to ground. We just take note of it on the way there. And that's the, for anybody that's heading down a pathway where you will someday study assembly language, that's going to be your jump on carry bit. So it's a very, very important thing. But you saw it solved that 0 thing. No matter which one we had, we got back to just one single 0. We got back to the number we started with. And we saw earlier, I should leave that up there. 0 is defined to be positive, and 1 is defined to be negative for us today. Just an arbitrary definition of those symbols. We had to pick one. that made sense when I first wrote it down. Some machines might reverse that, but we just pick which one's going to represent the positive, which one's going to represent the negative. So if we're adding these, well, just like we saw with base 10 a few moments ago, addition stays as addition. We can keep it that way. 1 plus 0 is 1. 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 1 plus 1 is 2. You've already seen all the combinations, right? 1 plus 1, 0 plus 1, 0 plus 0, 1 plus 0, 1 plus 1, and if there's a carry, maybe a 1 plus 1 plus 1. That's as much as we're going to end up with. So, somebody want to tell me what this number is? Just for quick practice with the binary. So 16, no 8s, plus 4. Which is what we get here if we add them, right? So we just add just like it was. If we subtract, if we're going to do 1, 1, 1, 1 minus 1, 0, 0, 0, to avoid all that carry stuff, which would mean building 2 circuits, which is, especially with the days of the MOSFET silicon, all that stuff small, all we really comes down to the engineer draws a picture and then basically use like the old style photographs, uses that picture to burn away parts of the silicon and crystallize some of it, oxidize some of it. It's just drawing a picture and doing that, but we have all those little bitty parts real close together. So if we have to make 2 circuits, then there's more chance of an error happening. So it'd be nice to do it as just 1. So that's where this 2's complement comes in. So instead of this, we can try adding the negative. 1, 1, 1, 1 plus, I'm going to write the negative sign, plus the negative 1, 0, 0, 0. And we have this definition over here. Our 15 is positive, our 8 is negative. So instead of this negative symbol, I'll do the positive and negative here. But we need to do our 2's complement. So the first step is we take the 1's complement. Our positive 15 stays the same because the complements give us our negative numbers. So the positive number stays like it is, 0, 1, 1, 1, 1. And the negative number, we need the complement, which is so much easier in binary than decimal, because, well, there's only 2 things. So the complement could only be one. There's only one option for what the complement is. The other one, which is actually a meaning, what complement means. One of the meanings of complement. Things complement each other, not the spelled with an I saying nice things, but the offsetting. There's only 2 options. So we do this, switch all the 0s to 1s and all the 1s to 0s, gives us the complement. Then we take the 2's complement of that to deal with the 0 problem. 2's complement, we still have a positive 15. And we need to add 1 to this, plus 1. So 1 plus 1 gives us a 0. Carry a 1, 1 plus 1 gives us a 0. Carry a 1, 1 plus 1 gives us a 0. Carry a 1. And then we end up with a 0 there. So if we add those together, 1, 1, 1, a whole bunch of 1 plus 0s, pretty quick to add, right? 1 plus 1, 0, carry a 1. And it looks like this. So this is where we would look at that other bit and use that to determine if we have a positive or negative number. We did 2's complement addition, so that means our symbol got complemented along. Our symbol got complemented along the way. So this is Yeah, that's right. So our symbol got complemented, so a 1 here means that we actually have the wrong symbol. It's not a negative number, it's a positive number. So we'll just discard that. And 0, 1, 1, 1, we saw earlier. Somebody want to tell me what that is in binary? Mhm. Which is what we should get when we subtract 15 from 8, right? Let me swap those around. I'll come back to like this point, and let's do 8 minus 15. So positive 8 plus a negative 15, I should say it that way. So we're all from one operation. So positive 8 is 0, 1, 0, 0, 0. And a negative 15 would be 1, 1, 1, 1, 1. So again, we need to take the ones complement. Ones complement, our positive 8 stays like it was. They're all ones, so those are going to become all zeros. And then adding 1 to that's pretty easy. So our 2's complement, 0, 1, 0, 0, 0. Adding 1 to that is pretty easy. 0, 0, 0, 0, 1. And then adding these two together is pretty easy as well. This 2's complement addition, which means our sign got complemented along the way. So this should actually be a negative one. So before we discard that, we're going to take note of what it is. We're seeing the positive sign, but we did complementary addition, which means we're looking at the wrong sign. So this is the 2's complement number. Or from life, you all probably know if you have $8 and owe somebody 15, you're still 7 in the hole, right? We have a negative number, and that negative number is in 2's complement. So we need to uncomplement that. So going back, to get from 1's complement to 2's complement, we added 1. So here we'll subtract 1, which is pretty easy in this case. 1, 0, 0, 0. That gets us back to the 1's complement, and the 1's complement, we just swap our bits. 0, 1, 1, 1. Oh, and then we do need to complement this sign somewhere along the way. Get back to that proper sign. So now we have negative 7. So you can see, hopefully that's enough to see that the patterns all work out. You can do more complicated ones if you want to, but we can do it all from one operation that way, which means build one circuit. So that's how we that's how what the computer is actually doing. The full adder piece is doing this. It's a small technicality that they don't in the early days of computing. If we started adding voltages, that can become a fire risk. But if we subtract voltages, the worst that could happen is the electricity goes away. We lose all of our electricity. So subtracting it was a lot safer, especially in the early days of computing. So negate all of this for what the actual circuit is doing. If we wanted to do 15 plus 8, we would take negatives all the way around. Swap the order, so we do -8 minus -15. So yeah, and it swaps around. So there's extra layers of circuitry, but we're humans, so we think about addition. Unless you're the electrical engineer making a full adder or an arithmetic logic unit, you don't need to worry about that technicality. But be aware that it's there. But as humans, we're going to think about the addition, and then we can just keep a counter, count how many times we add numbers together to get multiplication, or we have subtraction. So just count how many times we subtract numbers to get the division. and have the remainder there at the end. So we can build all of our mathematics up from one single operation. One circuit is what it comes down to. Do you have a question? Oh, it looked like you were raising your hand. That makes sense. Sort of introducing it, or maybe it makes sense is the wrong way. That wasn't too confusing, was it? Most confusing part's all those ones and zeros. We can deal with way more than that. I'm gonna go back to a conversion thing. Is it okay if I erase this? So 2's complement is, it was kind of a neat pattern that just sat on shelves for years until the binary state machines came along. And then in binary, the complement, since 2's complement, any complement is so much easier in binary. And we don't have quite as much confusing. The confusing part is all those symbols. Let's do another number. 147. I don't think we did that one earlier, did we? I can't remember what we did. I see some confused. I don't think we did that one earlier, but we'll go through the process. I've done that before, just making up numbers and made up the same number after break as I made up before the break. I guess it was like fresh on the mind or something. So to get to binary, 2 to the 8 would be 256. So that's how I know that 8's going to be enough here. If we had 312, we would need a 9th bit. 500, 2 to the 9th is 512, so we would have to go there. Or so you just use the range to figure out how many bits you need. This is less than 256, which actually with 8 symbols means with 8 symbols, since 0 is one of our numbers, with 8 bits, we can represent 0 to 255. So we're off by 1. There are 256 spots in 8 that we can represent in 8 bits, but we want 0 to be one of those spots. So we can only get up as high as 255. Or when we do 2's complement, we go from negative 127 to positive 128. 4, 5, 6, 7, 8. But for an integer, this can be represented in 8 bits. It's usually best to start with the biggest one. I guess you could do either way. I think it's best to start with the biggest one. We can tell it's an odd number, so we know there's going to be a 1. We only have one possible column where we could make things odd. But I find it best to start with the largest. So 1, 2, 4, 8, 16, 32, 64, 128. It's kind of easy to find those, but you've probably already been hearing those numbers over and over again your whole lives. So 128. Well, 128 fit inside of 147. The head nods again, so minus 128. What do we have there? 19. Basically do all the other stuff. I just rounded that. 148 would be 20 away, so it's got to be 1 less than 20 away. That's something that applies a lot in computers. That even if we do it in our normal shortcut way, we may not pay attention to it in daily life. But 147 minus 128, I don't see it immediately, but it's really close to 2 easy problems. 148 minus 128 is easy. And 147 to 148 is easy. So those 2 easy problems are easier than this one problem, even put together. That will apply a lot in your studies in computers. Lots of easy problems is much easier to deal with than difficult problems. I always use the words complicated and complex. Complex means lots of parts. Complicated is hard. Machines cannot do complicated things. Machines can only do complex things. Machines can only do lots of easy things. Oh, back to this. So we have 19 left. So 64, 32, those are way too big. We'll have a 16 minus 16 leaves us 3. So no 8s, no 4s, and we'll fill in the 3. 2 and 1 gives us 3. So the worst part of that for humans is all those columns. Because the machine needs the 1s and 0s, the binary states, but we can do way better than 1s and 0s. Or if we went the other way, if we started at I'll do a 4-digit 0, 0, 1, 1, 0, 1, 1, 0. We start adding these up. 60, 32 plus 16, 48. Don't have any 8s, and 4 would be 52, 54. So there's just lots of steps along the way with all that. We can do more. So it'd be nice to have an intermediate system, not have to work in binary. And this is one that you will do wherever you're heading in IT. If you need to work directly with the binary, it's too simple for the human mind. We need a more complicated system to represent that. So in order to line up to the machine, it has to be made solely of 2s. We can only make the number we want from 2s. So we'll start with 2. We know that's too small. If we square 2, so exponents, we can keep adding exponents of 2 until we find one that's better for us. 2 squared gives us 4. That's a little bit better. But as humans, we can deal with way more than 4 symbols, right? So let's check the next one. Square that. So 2 squared gives us 16. It's more than 10, but still, it's less than our alphabet. Still an easy, it's less than our fingers and toes put together. So that's not too big. The next number, we square that again, 16 squared would be 256. And if you ask a human if they could easily deal with 256 symbols, they're going to tell you no, but we really could. How many emojis do you know the meaning of? If you add those in your alphabet, capital, lowercase letters, your digits, you regularly deal the arrows. Anytime we see an arrow, even though arrows can mean the direction the arrow is pointing and the place it's going to mean something different, right? If you see an arrow pointing to the left on the interstate, it means one thing. If you see an arrow pointing straight down on the interstate, we know what they mean. Lots of meanings for that one symbol. If you ask a human if they could easily deal with 256 symbols, they'd say no, because it sounds like a big number. But we easily can. But it sounds big. It sounds hard. So let's back that off. So 16 seems like a good number to use. It's built only of 2s. So it lines up perfectly with binary. There's more digits. So it's closer to what humans are used to working with. And that's actually how we usually make that conversion. So a nice trick. So instead of doing this, well, I'll write out the basics of it. So it's called hexadecimal. I always forget whether it's an A or an I. I think it's an A, but I've forgotten and had to look it back up so many times that I've confused every time I write it down. Yes.
I have to go. I'll watch the rest.
Okay, yes. This actually makes everything easier. So to convert, we go from binary into hexadecimal, and then from there into decimal. The multiple steps is easier than the one big step. Also gives us a nice convenient thing. Before I show that, we need our symbols. Because with binary, we need 2 symbols. Decimal, like we're used to, we use 10 symbols. So with hexadecimal, base 16, we need 16 symbols. So still working with kind of building things up from numbers. 0 through 9 are obvious, but that leaves us short a few symbols. So A through F are what we fill that out with. And it's still pretty easy to count on one hand. I'll turn on the camera so that you can see what I'm doing. So we go to 10 like normal. 1, 2, I have 6, 7, 8, 9, but when you get to 10, think of 10 like this, and then 10 would be A. So A, B, C, D, E, F. And we can count up to our 16 symbols still to get used to it. So A or 10, B is 11, C is 12, D is 13, E is 14, F is 15, and then it's base 16, so 16 would be over in the a 1 in the next column. The base is always written 1, 0. This actually makes things a lot easier because it's 2 squared squared. 2 squared is going to be 4. So let me try to color code it. I'll grab red. So if we deal with this instead of all at once, let's just split it into 2 4-bit numbers. Then we have a 4-bit number here and a 4-bit number here. So 0, 1, 1, 0. So no 8's a 4 and 2 gives us a 6. And 0, 0, 1, 1. 1, 1's 3. So this is like 3, 6 in base 16. So 3 times 16 plus 6 times 1. 3 times 16 is 48. 6 times 1 would be 6. So that gets us back to 54 and a couple of easier steps. It's kind of like that thing earlier when there were 2 easier ways to do that problem. The 2 easier ways are quicker than doing the one hard way. We break it down into pieces. So anytime we're working with binary, we there's 2 symbols. There's also base 64 encoding. So you have lots of binary, like you have a photograph in binary. You have lots of bits. We use a much bigger system to make the string shorter. But pretty much, if we're working in binary, we do it with hexadecimal, which means we're working 4 bits at a time. Base 64 encoding would use 6 bits at a time. So we just, instead of all these 1s and 0s, we just look at a bunch of them at once. And it gives us a quicker way to convert things. So we have 8-bit numbers, 32-bit numbers. Each 4 bits of it, a 64-bit number, each 4 bits is 1 column of our hexadecimal value. So 1 0 1 1 1 0 0 1. So if we wanted to convert that number, first thing we want to do is take it 4 bits at a time. Split it up into 2 4-bit chunks, and then each one of those 4 bits becomes 1 hexadecimal symbol. And the hexadecimal can be written in 1 symbol. So 1 0 1 1. What is that number? Eight plus 2, 11. And so 11, but we want to write it with 1 symbol. So 9, 10, so A, B, so that would be a B, and 1 0 0 1, 8 plus 0 plus 0 plus 1, this is 9, which that's still a 9, so that number would be B9. Then we have 11 in the 16s column, plus 9 in the 1s column. What is that? 160 plus 16 is 176. 9 more from that's 185. So that'd be how we write 185. And see how breaking it down into smaller problems is easier than that original one. And we do sometimes have to work with binary, and it will almost exclusively happen with hexadecimal. Sure, we don't want to look at all those bits. Depending on the program you're going to do, maybe you're going into networking. dark room on the board anywhere. It's okay if I go ahead and erase this for some examples. So no matter which program you're going into, you will see hexadecimal a lot more often. So maybe you're going into network. So like NetE, server administration, the cloud infrastructure, CLDI. The program's new. I keep getting the letters wrong on it. Cloud infrastructure, and you're going to deal with IP addresses all the time, which those are how the machines know each other. The names the machines know about the machines' names for each other. We don't want to deal with all that binary, so I'll use version 4. IP version 4. There are lots of versions of that. Anybody heading to a 4-year degree, I can guarantee you have to write it. You will, if you're heading in one of these programs, you will read a 1,000 pages of textbooks talking about these protocols. And this was 19 lines of code. If you write those 19 lines of code, you'll understand more than the 3,000 or 4,000 pages of textbooks. If you're heading to a 4-year degree, you will definitely write those 19 lines of code. Usually, like IUS, they'll give it to you in C++, and you have to rewrite it in Java. UL does basically the same thing, only I think it's a different order. They're using mostly C#. So they probably give it to you in C++, and you have to rewrite it in C#. But coding up those 19 lines of code, you will understand it way more than several thousand pages of textbooks trying to describe it in English. But those have 4 8-bit numbers. So we have 4 sections. So like 123.10.8.4. So really what the machine's going to be using all binary. If we're working with that, we don't want to see the binary. So we could write all of those numbers in hexadecimal. So 10, I'll do the 10 first. That's a 8's still 8. That's still a 4. And we would do 2 digits because they're all 8-bit numbers. Each hex digit is 4 bits. So it would look something like this. Then 123 is 123 divided by 16 is 7 with a little bit left over. 7 times 16 is 112, so there's 11 left over, so 7A. So we would look at it something like this. For version 4, it would probably be we usually look at that in base 10 because they're all numbers 0 to 85. IP version 6 has a lot more digits, so that one's almost exclusively looked at in hexadecimal. But it takes a whole lot more to write on the board. And then to see what this is in binary, we just each one of those digits gets 4 bits. So 7, we already saw that a couple times. That's 0, 1, 1, 1. An A 10 would be an 8 plus 2. So no 4s and no 1s. So 1, 0, 1, 0. Dot, 0 is 0, 0, 0, 0. A, we just did a 10. 8 plus 2, 1, 0, 1, 0. 8 was 0, 0, 0, and 8 is 0, 1, 0, 0. Oh. 1, 0, 0, 0. Sorry, put the 1 in the wrong spot. But you see how quickly this goes over to the other ones. 0, 0, 0, 0, and then 4 is 0, 1, 0, 0. So by going through hexadecimal, we can get to the binary a lot quicker because we're only dealing with them 4 at a time. Our largest bit in hexadecimal is going to be 8. And you can do 8 plus 4 plus 2 plus 1 on your hands if you count your palms. Count your fingers too. It's only going to get up so high, so we can do that one pretty quickly. And it gives us a better way to work with decimal. If you're working and in somewhere like with programming, you're going to deal with colors. So a similar thing, red, green, and blue. If you remember back in elementary school, they teach you with paints, red, yellow, and blue. That's actually magenta, yellow, and cyan. So like reflected light, it bounces off something and then you see it. That's a mix of magenta, yellow, and cyan, but they usually tell us red, green, and blue when we're little kids. We probably don't know the other words, especially magenta. If we're looking at source light, that's a mixture of red, green, and blue. So if it's coming right from the bulb, or in our case, coming right from the LEDs on the screen, that's source light. With reflected light, you see what's missing. And with source light, you see what's actually there. Our eyes work differently between the two of them. But we mix red, green, and blue together. So those are often written in hexadecimal. So again, we have from 0 to 255, 8 bits for each one. So maybe we have 27 red, 134 green, and 82 blue. That would give us a dark blue. Let me switch this to 127 because that's going to work better for the conversion. Now it's a yellow. The first one was a dark green, a little bit of red, a lot of green, and somewhere in the middle of blues, kind of a forest green. Red and green mixed together to make yellow. And then this would kind of darken it up a little. Blue would darken it up a little in this case. But again, we can convert that. So 127 would be 7, 112, so that leaves 15 F. So 7F, 134, I think is actually the next one. So 134 divided by 16 is 8. So 8 and 8 times 16 gives us 128. So that leaves us 6, 8, 6. I just happen to know 16 times 5 is 80. So 5 in the 16 column and 2 in the ones column. So we can represent that with a lot fewer numbers. And we can also get that easy conversion where each hexadecimal digit is 4 bits. And the biggest number we have to deal with is an 8. So we're dealing with all numbers for all of them. So 7 is 0, 1, 1, 1. We've seen that a few times. F is our highest number. That's as high as we can get in base 16. So that's got to be all ones. 8, 1, 0, 0, 0. Already seen that a few times. 6 is 0, 1, 0, 1. Whoops. No, it's not. 6 is 0, 1, 1, 0. 5 was our starting example today. Right? 0, 1, 0, 1. We actually drew out the circuit board. And we're in base 2. The base is always 1, 0. So 0, 0, 1, 0. There we have the bits. So we work with the color directly here. That's important on color because if we're controlling colors, we are directly interacting with the LEDs on this picture. We're saying it's in this, turn the red up to this level and the green up to this level and mixing them. So we do that extensively with colors. But wherever you're heading, there are a few places where you need to work with binary. And the confusing thing about it is it's too simple for the human mind. So if we need to work with binary, we just work with it 4 bits at a time. That's hexadecimal. That makes sense. Everything there makes sense. See, it's not really new knowledge. Hopefully these are things you've seen before. In modern world, you've probably seen hexadecimal things. Like somebody said, here's a number, and you'll see F's and A's in there and not know what it was. But that's how we do it. It's too simple for the human mind. It's great for the machine, but that human propensity to make things more difficult than they need to be. We kind of have to do that for binary. So we just work with it 4 bits at a time instead of 1 at a time. Or 6 bits at a time if it gets really, really long. And base 64, we need more symbols, so it uses the whole alphabet. capital letters, followed by lowercase, well, 0 through 9 are first. Then capital letters, followed by lowercase letters. And that gets us, what, 62 symbols? 52 letters that we can use, plus 10 digits. So then we have 2 more, and it will go, the last 2 change. You'll have to, if you ever work with base 64, you have to figure out what the last 2 are. But it goes left to right on your QWERTY, QWERTY setup. Go left to right, shift first. So it might be minus plus or underscore subtract. You'll be able to figure out what the last 2 symbols are because there's only 2 more. So just look for the 2 symbols that aren't a digit or a letter from the alphabet. And whatever the other 2 symbols are, left to right, and the shift one happens first. So just like the capital letters come before the lowercase letters. And then it translates the same way, just 6 bits at a time. So that's our numbers. And to represent letters is, we can just use those numbers directly. So we want to represent a capital A. Let's say we'll use 65 for that, which in binary is 64 plus 1. 64 is one of our columns, so we just get something in that 64 column, and then we just need a 1. 32, 16, 8, 4, 2, 1. So there's 60. So A's, capital A is 65. A capital B is 66. Capital C is 67. Do y'all see where this pattern's going? So on and so forth. And I always remember lowercase e's. I just remember a few of them. I remember lowercase e, capital A, a handful of them out there. But we can just do a one-to-one correspondence on all of our things. So if we had a space, can't really draw a space on the board very well, so I'll just write the word space and say that's number 32. And then go through the rest of our symbols the same way, give them a one-to-one correspondence. A line feed is number 10. There's a bunch of them. So let me pull this up on the screen. So that's ASCII code. American Standard Code for Information Interchange. So much of the work was done in America, in England. There's that secret project in World War II, and immediately following that up. So America and England and our allies, tons of work was done in Norway. And they don't speak English, or they speak Norwegian, but they also all speak English. Because pretty much it's just English speakers that don't bother to go in other languages. Most of the rest of the world is kind of required that you know a couple. You have to learn several languages, not just one. But it always seems, so yeah, most of it was done with the American alphabet first. They used 8 bits, or great for the American symbols, 0 through 255. It's more symbols than we normally use in America. Well, actually, there were still a few missing. We got quite a few, but definitely not for the whole world. So it went to a bigger system, which is Unicode. But it didn't, Unicode didn't, like, they didn't throw this away and replace it. Unicode is an extension. So the first 256 characters in Unicode are ASCII code. They just extended it instead of going back and starting from scratch. So in America, we'll often refer to ASCII code, but really we're using Unicode. So you just want to go look up a Unicode chart. Unicode chart. And look around for one of these, because you're heading into IT, you'll want some, and you probably want one that's nice to read. That's probably not the one you want, right? Look at lots of different ones. I want to make sure we'll show you how to read this way that sort of abbreviates them. There's a common way because it takes up less space. And I want to make sure y'all know how to read the ones that take up less space. And that was gonna finish up what's here for today. So lots of charts. I guess this one's like, okay, yeah. So here's Unicode. These are hex digits, so 4 hex digits followed by 2 more hex digits. The rows are going to be your first one. I want to look at it in ASCII code, and then the columns are the last 4. Maybe I should look for one that has ASCII. That way it only goes up to 256. So that one happened. Oh, that one's just written straight out. Now that I'm looking for them, I'm having trouble finding one. Okay, this one shows it. Let me move the zoom thing off. Right. So as it goes on, I grab my little pen, and from 10 on, we would probably be thinking hexadecimal, right? A, B, C, D, E, F. So each one of those, that's our first hex digit. And then the second column, or sorry, the rows are the first digit, and then the columns are the second digit. So if we wanted to say 3, 5, we come to 3, and then over to the 5 column, and that would be an S. Or F. It looks like only half the charts here. We'd go to F in the first column, and then over to F, or F in the row, and then over to F in the column. Everybody see how to read those? That's a more common way to see them, a very common way to see them, because it takes up less space than trying to write every single one like this, where you just make a list of all of them. That takes up a lot of space because you have to repeat those digits. So especially in books, it takes up way less space, way less of the page. Or Unicode can be made to fit on one page in a book. With books being a little less common. Does this one have all of them? Nope, it just has the values, it doesn't show the header labels. And you can see the first 32, 0 through 31, those are control functions. There's different ways to do 0 and 1 written, but that is just 0 and 1. If you're manually coding something, you can go turn bits like actually typing character 0 in it, like ASCII character 0. There's a beeping sound, line feed, carriage return, HT for horizontal tab, VT for vertical tab. We don't really use that. We don't have one on our keyboard, but there is something that does. On typewriters, there was a vertical tab as well as a horizontal tab. We tend to only use the horizontal, only keep the horizontal one around. BEL is bell, so that's a little beeping sound. Acknowledge is a 1-bit thing, so when you're communicating across the network, it does send back the acknowledge thing. So that is a specific symbol. And then we get into our characters, and they build up from there. Look for a chart that you like, because you will need it somewhere on your way through school. Probably Unicode. ASCII is just the beginning of it. And Unicode has all the emojis and stuff in there. Don't want to remember what those are. Originally, it was an extension from 8 bits up to 16 bits. And that covered a lot of language, a lot of the human symbols, but not all of them. The example I always go with is Egyptian hieroglyphics. If you want to actually use your keyboard to type in Egyptian hieroglyphics instead of inserting pictures, you would have to get up to 32-bit ASCII. So it has been, or 32-bit Unicode to get up to that many characters. So there's lots and lots of them, but they're all extensions from each other. They didn't start over at the beginning. Not since 1947 when they developed ASCII. So for Americans, if we're in America, working in America, you probably start with an ASCII table, but look for a chart that you like, because there's lots of layouts, lots of colors, lots of patterns, and it is something that you will end up spending a lot of time staring at. So find the type of chart you like, and maybe what keywords in the search will result in that type of chart. Y'all know that routine. Yeah, I have some tips for search engines and stuff we'll see soon. Does that binary stuff make a little more sense for those who haven't seen it before? It's really easy. It just looks like because we're all the symbols, but we can't do hard things with only 2 symbols. 2 symbols isn't enough to represent anything hard. That's one of the nice things about studying computers is machines can only do the simple things. So we aren't going to be doing anything complicated. It just seems that way when we're first starting out because we don't see what it's doing. But if you take your time and learn it through in the proper order and all that, build it layer upon layer upon layer, kind of like the way the computer's doing stuff. Only studying simple things with IT. Because yeah, machines can't do hard things, at least not yet. Even when we get up to AI, they can do it really, really fast. They can do lots of things really, really fast. So it looks like they're doing something hard, but it's still lots of simple things, kind of like the breaking it down into a 2 simple problems instead of 1 hard problem. Anybody have any questions about that? Okay, I just wanted to cover that because the courseware is actually a major course learning objectives. You won't be tested on that in this course. If y'all haven't noticed yet, I'll teach more than I test you on. I'll fill up all the time with things that are interesting. Even when we finish the exams and all the questions that you're going to be asked for this semester, I'll still find some interesting things to talk about at the end. Because I like to teach more than I test you on. This is one everybody will see, and the course where it's actually listed as an objective is loaded down with stuff, so it's very overwhelming. But it's been a few seconds since I asked if anybody had any questions. I don't hear anything. If you have any, let me know. Otherwise, on Thursday, we will start looking at data the way we would represent it. So writing it in documents and spreadsheets and databases and files and yeah, the part we actually work with. The human level of abstraction on top of all those on and off switches. I'll see you all Thursday. Have a good one.